Well, hello again. This is Chapter 7, the start of Chapter 7. This is the lecture. This chapter is called Uniform Circular Motion and Gravity. And this is actually one of my favorite chapters of the fall semester because it combines really all the physics that we have to date of Newton's laws of motion, especially F equal ma, into Newton's laws of gravity, which we will talk about in this chapter. So to really start off, though, we have to talk about what's called uniform circular motion. And the chapter starts on page 217, and there's a couple pages where it talks about uniform circular motion, and in particular there's some diagrams on page 218. We need to pay particular attention to these diagrams on page 218, and in fact I'm going to talk quite a lot about these two diagrams on page 218 and give a lot more detail that's actually given in the book. When we talk about circular motion, we have to talk about what's called centripetal acceleration, and the book talks about that on page 219 and then up to 20 to 221 and finally 223. But before we talk about centripetal acceleration, let's look at, in particular, at the diagrams that are on page 218. And we need to, some of this is going to be review, but we're going to go over it and then go a little bit farther. Okay, if we have circular motion, suppose we have an object, and here's the center, and we have a mass here, and there's a string here, and we're flinging this thing around in a circle, right about the circle, and this is a string. Okay, you can imagine taking a string about a couple feet long, tying a rock to it, and then spinning this rock around with the string. Okay, the string, let's assume we can't keep the constant radius. R, here's radius, about the center. And at one moment, the rock is here. At another moment, the rock is here. At another moment, the rock is here, and it keeps spinning around. Okay. Let's define some terms here. Suppose at t equals 0, right here, the rock is right at this mark, and the rock comes around and it meets this point again at t seconds. Okay, so t seconds, we'll say it from t equals 0 to t, it makes one revolution. Okay, and maybe this t, just as an example, let's say this t is 2 seconds. So it makes one revolution every 2 seconds. One revolution, two revolutions would take 4 seconds, 3 revolutions would take 6 seconds, etc. This t, then now, we call the period. The period of revolution. The period is defined as the time for one revolution. Now, if we take, let's say you take this rock and now you spin it faster. I'm going to change the period. Let's say the period now is 1/2 a second. Okay, so it makes one revolution every 1/2 a second. Okay, we're going to define the frequency. We'll say F. F is defined as the frequency. And F is, the frequency is the number of revolutions per second. Okay? So, which would be what? Remember, this the period here is 0.5 seconds. We could say per revolution. Or we'll write it this way. T is 0.5 seconds per revolution. ReV. ReV we'll use for revolution. Well, notice for the frequency, we define as the number of revolutions per second. It's really the inverse of this. So we say the frequency is 1 over the period, which would be 1 over 1/2. The period is 1/2 seconds per revolution. So if we divide this, we obviously get 2, and we flip this, and we get revolutions per second. So this works. So we say that the frequency is 1 over the period. This is an important equation. We will use this in this chapter, but also in the lab. I think the book, you know, I can't remember if the book talks about this or not. Let me look real quickly. I think it does. Actually, it does. Flip over to page 235, way in toward the back of the chapter, and you will see this equation. The frequency is 1 over the period. Actually, it's on the top of page 236. So instead of saving this for the back of the chapter, I think the author really should have just described this at the front of the chapter. So, because to really talk about circular motions, we have to talk about the very basics of revolutions, periods, and frequency, things like that. Okay. So, as an example, suppose I really spin this thing fast, and let's suppose that the period is 1/10 of a second. So it takes only 1/10 of a second in order to make one revolution. What would the frequency be? Well, the frequency would be 1 over the period. The period is 0.1, so a 1 over 0.1, 1 over 0.1 is 10, okay, which makes sense. It makes one revolution in 0.1 seconds, so therefore it makes 10 revolutions in 1 second. So that's what the frequency is. The frequency is the number of revolutions per 1 second, okay? All right, now that we have that down, I'm going to erase this right now. Okay, so this is all about circular motion. I'll just write that down. Circular motion. So one of the things we know about circular motion is that the frequency, the frequency is 1 over the period. Okay, I'm just going to write that equation right there. Now, another thing we know about circular motion goes back to an equation that we introduced some time ago that I hope you remember, and that's S equal R theta. If you remember, S is arc length. This distance, suppose you're only going to look at it, you're spinning this rock around, but you're only going to look at a portion of the arc. Say, when the rock goes from this point to this point, from A to B, it spins through a certain angle, theta. This distance, the arc length, is the actual distance that the rock travels from A to B. So S is, again, arc length. R is the radius. And you remember theta is the angle in radians. Do you remember radians? If you try to use this angle in degrees, this equation will not work. This only works when theta is in radians. So for all of this chapter, I believe for all of this chapter, whenever we use the angle theta, we're always going to be using it in terms of radians. Radians are actually, in general, for mathematics and for engineering and for physics, generally, whenever you see a theta, it's generally, especially in this form, it has to be in radians. Now, and remember, 360 degrees equals 2 pi radians, which means if you divide by 2, this is how you convert 180 degrees equals pi radians. You will hopefully remember that. And so if I have 30 degrees, in order to convert 30 degrees to radians, I multiply by pi radians divided by 180 degrees. Okay? I simply multiply this out, and I would get some number of radians. So this is how I would convert, I'm not going to do it, but this is how I would convert from degrees to radians. Okay, what we're going to do is we're going to use this equation here of S equal R theta, which is one of the most, this is one of the most fundamental equations, S equal R theta, for circular motion. It's very important. Now, let's say that we go, when you're spinning this rock around, it goes from A to B. We travel from A to B in a certain time in delta t. Delta t is some number of seconds. Okay? Or it may be a fraction of a second. In fact, it may be a very short amount of time, but it's some amount of time. We'll call that time delta t. Okay? What we're going to do is I'm going to take this equation and I'm going to say this. This S here, I'm going to just give it the name. Instead of calling it S, I'm going to call it delta S, which means that it's just a small, that maybe the S refers to the whole circumference, and a delta S just refers to a short segment of it. In fact, it just refers to this short segment. Okay, so delta S, which is a small segment of arc length from here to here, equals R times delta theta. And again, if I make this a delta theta, it means I'm just changing the angle by a small amount. That small amount, I'm just going to give the term delta theta. Okay? So, what I've done here is to just introduce, I'm starting to introduce the idea of calculus, but I'm not going to invoke calculus, but it really comes about this way. Really, this is S equal R theta. Same equation, S equal R theta. And all I'm simply saying is that instead of making these a big angle, I'm just going to make them a little angle. And if I change theta but by just a little bit, I'll call that delta theta. I will change S by a corresponding little bit called delta S. Okay? So a small change of delta theta times R gives me what the corresponding arc length is, delta S. This could be, for instance, suppose I'm here and I could, just an example, and I only change a very small amount. Here's my delta theta. The arc length that I change from here to here would simply be delta S. Okay? So, now, I'm going to take this delta S and I'm going to divide it by delta T. Now, if I divide the left-hand side by delta T, I have to divide the right-hand side by delta T. And because this is an equation. So if I have to do the same thing to both sides of the equation. So, now, all I'm doing is I'm dividing the left-hand side of the equation by delta T, then I divide the right-hand side of the equation by delta T. Now, I want you to remember all the way back to chapter 1 where we talked about the idea that the distance is the velocity times time. Pretty basic equation that we've been using. And also, I'm going to write it up here, therefore that the velocity is the distance divided by time. Okay? So, if I have the velocity here, well, if I come in here and say I have a small change in distance divided by a small change in time, that still gives me the velocity, right? So that's exactly what this is. What delta S is, delta S here refers to the actual length, the actual arc length that this mass is traveling. It's the length. This is actually in meters, right? So it's the same thing as x. So delta S divided by delta T is simply velocity. We call it velocity. In fact, we will give it a name, tangential. Tangential velocity, meaning it's the actual velocity of the rock as it flies at the end of the string. That's really how fast it's going. If it travels 1 meter in 1 second, that's a velocity of 1 meter per second. So, and why do we give it the term tangential? We give it the term tangential because it's at the tangent, it's at the end of the string, and the rock is flying tangential to the string. That is, let me illustrate one little thing. If we suppose the rock was flying around, and at this point we cut the string. The rock is coming around. Here's the rock, but suddenly at this point you cut the string. What's going to happen to the rock? It's going to, at this point it's flying this way, it's going to keep on flying. The rock will keep on going in a tangential direction. That's why one of the reasons we call this the tangential velocity. In any case, we're not going to cut the string. We're going to keep on. The string is going to keep on going around. And the string's radius is going to be constant. Okay, so let's look at this equation. The tangential velocity, and I'll write it here. The tangential velocity is delta t divided by delta s, which is also, now r here is a constant, so I'm going to say r times delta theta over delta t. Okay, so r we're going to assume is the radius, that's fixed. That number doesn't change as long as we keep the string at constant length. Delta theta over delta t. Now this is given, let's look at this term. Basically what that means is that look, if when the rock spins from point A to point B, it travels through a certain angle, and it travels through that angle in a certain length of time. So what are the units of this? Delta theta over delta t. Remember, theta is in radians, so this is in radians per second. Okay, radians per second. This is given the term, we'll call it omega, which is angular frequency. Okay, and if we, well, let me write that down. Angular frequency, and it's given the Greek symbol omega, or I write it as W, but I think it, is that right? Omega. I'm shaky on my Greek, to be honest with you. I think that's right. If we look on page, let's see. I kind of forget where all this is talked about here in the chapter. You know what? This equation, this is not even talked about, unfortunately, until chapter 10. Sorry about that, but we're going to introduce it early because it's very important. It is introduced in chapter 10, at least I believe it is. So this term should be introduced in chapter 7, but the author doesn't. But we're going to introduce it now because it's very important. Angular frequency. Now come up here and look at let's compare the two types of frequencies. This frequency here is 1 over the period is the number of revolutions per second. Okay, so for instance, we could have, I'm going to erase this right here, we could have, let's say, 10 revolutions per every second. Okay, so we would understand that. There's 10 complete revolutions per second. Now, what angular frequency is it's the number of radians per second. So, how many, I'm going to erase this right here, if we have a frequency of 10 revolutions per second, how many radians in one revolution? Well, in each revolution, one revolution, there are 2 pi radians. Okay? So that, I'm going to erase this right here. So that gives us, notice that the revolutions cancel out, and that gives us 10 times 2 pi, which is, I'm going to go ahead and just multiply that out. 10 times 2 times pi, which is 62.83 radians per second. And that is exactly what this omega is. This is omega. It's the number of radians that this rock is spinning around per second. Remember, one complete revolution, is equal to 2 pi radians. Okay? So if this were just doing 1 revolution per second, then obviously we would just have 1 revolution times 2 pi, and we would simply have, I just changed the decimal point, we would simply have 2 pi radians per second. 1 complete revolution per second. So what we say is, from this equation here, that the tangential velocity is equal to the radius times omega, where omega is the number of radians per second. Okay, so this equation here is a very important equation for circular motion. It tells us that the tangential velocity is equal to the radius times what we call the angular frequency, and the angular frequency is nothing more than this. It's the number of radians per second. X number of radians per second. Okay? So I'm going to take this up here, and we're just going to work with this just a little bit more. When at first you're introduced to this concept, it takes a while to get used to circular motion, but once you get used to it, it's not so bad. It's really just getting used to the terminology. Okay? So the tangential, and I'm going to write it V tangential, just to remind us that this is a tangential velocity, is equal to R times omega, where omega is the angular frequency. And over here, we know that, just from what we did before, that F times number, if we have F and we multiply this by 2 pi F equals omega. Okay? And again, if you get confused about that, just remember that 2 pi times the number of revolutions per second. There's 2 pi radians, radians per revolution. The revolutions cancel out, and this gives you number of radians per second. So 2 pi F equals omega. So we can actually come in here and say omega, this is the same thing as R. Omega is 2 pi F times 2 pi F. We could say that. And we can also say, remember, frequency is 1 over the period. So we can also come in here and say, I'm going to put this over here, 2 pi R. F is 1 over the period. Okay? So the tangential velocity is also 2 pi times R divided by the period. Okay? You should be able to know these equations and be able to work back and forth with these equations in different form. Okay? In some cases, you will need to know the period. In some cases, you'll need to know the frequency. So I hope this isn't confusing. After you use these terms for a while, you will undoubtedly get used to them. Okay, let's actually work just a quick little example, because at first these concepts can be a little tricky. Let's say the radius is 2 meters, and you're spinning a rock around, and it takes, let's say, 0.1 second per revolution. So you're spinning this thing around 10 times a second, and it has a radius of 2 meters. Okay? Let's figure out what the tangential, well, let's basically figure out everything. Okay? The frequency is 1 over the period, which is 1 over 0.1 seconds per revolution. So the frequency is 10 revolutions per second. Okay, that should be obvious. Okay, the angular frequency, what we call the angular frequency, which is 2 pi F, it's simply, oh, I should use the big F, doesn't matter. whatever you have the frequency, you just multiply it by 2 pi. So it's simply 2 pi times 10, which gives us that 62.83, I think, radians per second. I think that's right. 20 times pi, 62.83 radians per second. So that would be the angular frequency. Okay, it's this number radians per second. Okay, what would be the actual tangential velocity? This is a tangential velocity. The actual velocity that this rock is really seeing as it flies around. The tangential velocity, we can say, is r omega. We can use that. We can also use a term. We can use the idea that it's well, r times 2 pi f. We can use that. We can also use 2 pi r over t. Any of these will work. Let's use this. The radius is 2 meters times the angular frequency